Similarly, for other particles of masses m2, m3, m4, and so on, at distances r1, sorry, at distances r2, r3, r4, and so on, the moments of linear momenta are m2 r2 square omega, m3 r3 square omega, m4 r4 square omega, plus mn r square omega. Okay, these are the individual moments of linear momentum. Now, if we sum up, if we sum up, if we sum all of them, then we'll get the net momentum, momentum of the body rotating about an axis. Okay, after this, the sum of all these moments of momentum gives angular momentum gives angular momentum of the body. We did J at the right. J equal to M1 plus M2 square omega M3 R3 square omega and then Rn square omega. Now you can take omega common. So within bracket we'll get Mn R1 square plus M2 R2 square up to Mn R1 square, Mn Rn square. This entire gives sigma Mr square. When you get the summation Mr square, the summation Mr square is I, so J equal to I omega. So remember the straight line motion we used to say equal to every. So on the similar basis in rotation we can say J equal to I omega. The role played by mass in straight line motion, the same role is a moment of inertia. In straight line motion we have velocity. Here it is angular velocity. Momentum, angular momentum. The J equal to I omega. Very important expression to be remembered. Once you have copied, please let me know so that I can proceed. Thank you, Puneet. Okay, this means all are working with me. Very good. Requesting you all to please write the next heading. Relation between torque and angular momentum. Relation between torque and angular momentum. Please write. Let a body rotating about an axis under the action of torque, under the action of torque, within bracket write it torque, with constant angular acceleration alpha, with constant angular acceleration alpha. So stop. We know that tau equal to I alpha. In earlier classes, we had derived this tau equal to I alpha. Now, tau equal to I, what is this alpha? Angular acceleration. It is rate of change of angular velocity. So this alpha can be written as d omega by dt, equation number 1. Okay, next line. The angular momentum of body rotating about axis. The relation that we had derived just now, J equal to I omega. J equal to I omega. Next line. The rate of change in angular momentum. So we differentiate this with respect to time. The rate of change in angular momentum. dj upon dt. So we differentiate this equation with respect to time. Now, right hand side, there are two terms, I and omega. So, how do we say that? For two complete graphs, while differentiating, we apply product rule. I agreed. But keep in mind, we have to differentiate I and we have to differentiate omega. I is moment of inertia, which is only mass and distance dependent. It has nothing to do with time. Okay, so I is constant. So d by dt I omega. Now I was already mentioned that I is constant. It comes out. Differentiation is applicable to omega only. So dj by dt equals I d omega by dt, which is number two. Let us see first and second. We are writing sides are same. I d omega by dt, I d omega by dt. And from first and second, we can say tau equal to dj upon dt. This expression is similar to Newton's second law of motion. Hope you remember F equal to dp by dt. So this is another relation which justifies the comparison between straight line and rotation motion. The role in straight line motion, force plays the same role is placed by torque in rotation. P linear momentum, J is angular momentum. There we used to say force is equal to rate of change of linear momentum. Here we'll say torque is equal to rate of change of angular momentum. If you all have understood this concept, come up. If no one, if anyone has not understood, then this is the right time to ask your query. Okay, these terms simply suggest that the idea is clear. But keep in mind, rate of change of angular momentum at the top. And this is the relation between tau and J. Okay, thank you, Avichet. I've seen that. Requesting you to please conclude the statement. The rate of change of angular momentum, the rate of change of angular momentum of a body is equal to the external torque is equal to the external torque acting on the body. Now, next important heading, please, right? Conservation of angular momentum. I'm going to use this expression. Conservation of angular momentum. First, please write the statement. If no external torque is acting upon a body rotating about an axis, upon a body rotating about an axis, comma, the angular momentum, the angular momentum of the body remains constant. Angular momentum of the body remains constant. Okay, will you write? J equal to I omega equal to constant. J equal to I omega equal to constant. This is called law of conservation of angular momentum. This is called law of conservation of angular momentum. Next, right? Proof. We'll do the proof and we'll do the applications of law of conservation of angular momentum as well. And give some applications. Now, how to prove it? We make use of the expression that we had derived just now. Tau equal to dj by dt. Okay, please write. We have studied that the rate of change of angular momentum, it comes under proof. We have studied that the rate of change of angular momentum of a body rotating about an axis is equal to the external torque. To start mathematically, the statement that you wrote, mathematically it means dj upon dt equal to torque. Differentiation of angular momentum with respect to time equal to torque. Now, what the definition says, if external torque vanishes, if torque equal to zero. Body is rotating, but no external torque is acting. Then, when we put torque equal to zero here, dj upon dt equal to zero. Now, maths and non-math students, please remember, whenever the differentiation of a quantity is zero, the quantity acts like constant. Some of the kids ask, sir, how we can say that the differentiation of constant is zero? If dj by dt is zero, then how you are so sure that j is constant? Let me give the explanation for this as well. dj upon dt equal to zero means j is constant. How? Just take this dt to the other side. So we come to dj equal to zero. Because dt into zero turns to zero. dj is what? Change in angular momentum. And what this is saying, change in angular momentum is zero. It means angular momentum is not changing. Okay, so dj equal to zero simply means equal to constant. This is for your remembrance. But keep in mind, generally, dj upon dt equal to 0, straight away it can be written like j equal to constant. If this is clear to everyone, quickly thumb up so that I can proceed further. Good to see that most of the kids are paying attention to the work being done here. So j equal to constant. Okay, now we know that. J is I omega. So I into omega equal to constant. Now what does it actually mean? I omega equal to constant. What it means? It means if you reduce I, omega increases. Okay? If I decreases, omega increases. Or vice versa. Vice versa means the reverse is also applicable. Or vice versa. Now, what does this actually mean? What are the applications of this? Now, let me take certain examples. Okay, so this simply explains. These examples matches with the condition. Keep in mind, if you decrease I, omega increases. First example. Now, imagine a stone tied to one end of a thread and it is being revolved. Okay, I hold it in my hand and if I revolve it like this. Okay, so stone is actually moving with certain velocity, angular velocity. Now, simply, while rotation, straight your finger so that the thread starts wrapping around your finger. Okay. While rotation, what I'm saying, just make your finger straight so that the thread starts wrapping around your finger. The thread starts wrapping around your finger. Now, observe that situation. When the thread is wrapping around, then what you will find, the radius of the circular path goes on decreasing and the angular speed with which the stone is rotating about the finger keeps on increasing. The stone takes quicker and quicker motion. As soon as the class ends, you can do this. This one is very simple. The logic is quite clear. You are decreasing radius. Mass is still there, radius is decreasing. Moment of inertia is radius dependent. So I decreases, when I decreases, omega increases side by side. That's why the revolution speed, the angular velocity of the stone goes on increasing. Okay? The other way to depict the same, you can do it by using another example. Just take a pen, remove the ripple from it. Okay? So it's a fine bone cylindrical shell, ripple removed. Okay? Then take the same thread, same stone, pass the thread to this board, okay, so that half of the thread is lying here and stone is here. Now rotate this, okay, thread, stone is rotating. Now start pulling the thread slowly. What you will find, the speed of rotation, that is the angular speed with which the stone is rotating, goes on increasing. The reason is same. Radius is decreasing, R decreases, omega increases. If these two examples are clear to everyone, come up so that I can proceed with my next example. Oh, good to see that everyone had understood. Is there anyone who's finding it difficult to understand the logic? Okay, now third example. Can anyone tell me what is somersault? Somersault. Anyone? Have you seen person doing somersault? Have you seen a sport in which a swimmer jumps from a plank which is at higher level into the swimming pool? While jumping, the swimmer generally folds his body, his or her body. And before entering the water, before entering the swimming pool, the person unfolds his or her body. As soon as the person jumps from the plan, the person folds his body. As a result of this folding, the moment of inertia of the body decreases. I decreases. If you observe, then the rotation, the speed with which the person is rotating and falling shoots up, it increases. And before entering the water, the person unfolds the body. While unfolding, moment of inertia increases, and according to the logic, when I increases, omega decreases. So before entering, the speed of rotation decreases. You must have seen gymnastics. Some of the athletes, some of the gymnastics are so much comfortable with somersaults that they can even take a number of somersaults directly in air and then they stand straight on the other side as well. It is the matter of practice. Okay, I know the logic is clear. Here on the process. Let's please make sure that all these things require a lot of practice. Okay, please don't know that as soon as the confidence you start doing the sort. And Sir had explained us that it's pretty easy just to hold the body. Our speed increases, we unfold it, our speed decreases. Okay, remember all these are done under some, you can say, you need some proper guidance to follow these conditions. Physics says I decreases, omega increases. If you increase I, omega decreases. They are having a vice versa relation. And somersault is one of the example. Third example, which is based on law of conservation of angular momentum. Now, any query from your side? This is the right time to ask. Any query? Okay, this suggests that you all have understood the concept. God bless you all.